So in the previous video, we were attempting to find the derivative of a, treating r as the variable, thinking about t as a constant. So these two problems are fairly complicated in the sense that we have to really be careful about what we identify as consisting of variables and what we consider consisting of constants. So t is treated as the constant here, which means the exponent in this function is the constant, and r is the variable. So actually everything inside of that parentheses is a variable expression. This is a function of a variable, and so we've called that stuff. Because what we really see when we simplify this is we have 100 times stuff to the constant, which is kind of like saying 100 times x squared. Well, what's the derivative of that? Well, it's 100 times 2x to the first power. We're doing the exact same thing here, except the problem is that what's inside the parentheses is not just x, or in other words, not just r, but it's a combination of r and a bunch of other little bits and pieces. So we have that's 100 times the constant. Okay, well, that's 100 times 2 stuff to the constant minus 1. So stuff in this case is just 1. But in our case, stuff consists of 1 plus r over 1200. And so we've kind of done it symbolically here. So now we take constant to the minus 1 power times the derivative of stuff. Okay, well, this might look complicated. What's the derivative of 1 plus r over 1200? Well, 1 plus r over 1200 is the same thing as 1 plus 1/1200th times r. Okay, that's a linear function. Derivative of a constant is 0. Derivative of something constant times variable to the first power is just the coefficient, and so this is times 1/1200th. Okay, so there are our two partial derivatives. Again, very sophisticated looking. And now we can say, well, what is this actually telling us? Well, in this case, we're studying the relationship between a versus r. So if you tell me what the current interest rate is, and you tell me what the current how much I'm going to be investing for, I could tell you what effect changing my my interest rate by 1% would have. So if I now go into this, okay, so using the notation, this is really just a of r of, rt is equal to this up here. So a derivative of a with respect to r of 5 and 10, now we can plug in our constants, will be 100 times 12t, which is 100 times 12 times 10, times 1 plus 5 over 1200 to the 12 times 10 minus 1. Well, 12 times 10 is 120, minus 1 is 119, times 1 over 1200. Okay, so we will go ahead and jump over to a computing system so we can calculate this, and we get, let's see, jump to the next line here. So 100 times 12 times 10 times 1 plus r over 1200 raised to the 120 minus 1 power, all of that multiplied by 1/1200. And I get 16.4. Okay, 16.4. So what does that mean? What is this telling me? 16.4. Well, again, this is a rate of change. This is the change in a with respect to a change in r. 16.4 is the same thing as 16.4 over 1. A is measured in dollars of future value, and r is measured in percentage of interest. So this is telling me that if I increase my interest rate by 1%, if my interest rate had been 1% higher, so approximately 6 instead of 5, then my balance would have been $16.40 higher. So the question is, does it make more sense, no pun intended, to increase your interest rate by 1, or does it make more sense to increase time by 1 year? Well, let's figure this out. So for a derivative of a with respect to t of r comma t, that's this function up here. So the derivative of a with respect to t when interest rate is 5 and time is 10 years is going to be 100 times the natural log of 1 plus the rate divided by 1200 to the 12th power, all multiplied by 12. Okay, excuse me, 12t. We forgot a t up here. 12t, because that's our stuff. And so now we can go back and calculate this. We can say 100. Now, in computing systems, a lot of times log is measured, log is actually log base e. So well, in this computing system, I just need to type in log, and that's understood by the computer. That's the natural log, excuse me, 100 log of 1 plus 5 over 1200 to the 12 times t power, oh, and back here t was 10. So to the 12 times 10 power, all multiplied by 12. In my mistake, I mistakenly again transcribed this incorrectly. It's 100 times the natural log of the constant. So in here, I should shove in 100 times the natural log of 1 plus r over 1200 times the natural log of 1 plus r to the 1200th to the stuff times stuff prime. And so I should have in here natural log of 1 plus 5 over 1200. And let's see how that changes things. So, oh, I don't need that natural log there. Okay, so let me change this to 1 plus 5 over 1200, and I get 8.22. Okay, well, what is that telling me? Well, that tells me that if I were to write this down, 8.22, and that's over 1. A is measured in dollars of future value. T is measured in the number of years. So if at the current state of things, if I were to increase my investment time by 1 year, then I would expect to see an increase in my balance of $8.22. So in this case, it makes a bigger difference, actually twice the difference, if I were to be able to find an investment that offers 1% more. Then, well, one, I wouldn't have to invest quite as long, and I'd make double the amount of money that I would if I were to invest 1 year beyond the 10 years. Kind of a tricky example, something to look at a few times, and my mistake over here, we did the derivative correctly, we wrote it symbolically, but then I transcribed it incorrectly, so that was my mistake. So we do have a significant difference here, and we do have a fairly complicated problem. So this is just a way we could use derivatives to try to understand and make sense of some compound interest functions. The one last thing we'll mention, and we won't explore here, but where would we go next with this? What would we do with all of this new knowledge? Well, what we would now think about is if I have a function, let's say z, that depends on 2 variables. So maybe my profit depends on the number of units that I sell and the amount of advertising that how much money I throw in advertising. So number of units that I sell and the amount of advertising that I do, or maybe it's not the number of units. Maybe what forces me to sell more units is the fact that I advertise more. But maybe I advertise on TV, how much I put in advertisement dollars on TV, and then how much I put in advertisement dollars on maybe radio. Okay, so now we have P, R, T, and maybe what I want to ask is, can I maximize my profit? Well, in our introductory calc course, we certainly can do this if there's only one input variable. We could find the maximum profit, and we find that point, and we figure out what input that corresponds to. Okay, and then what is that maximum profit? The problem here is that we actually have a 3-dimensional function. So if you think about 3-dimensional functions, they could be parabolas in 3-dimensional space. Now, I'm not good at drawing 3-dimensional functions, but if you can kind of imagine this as being a bowl, now there's variation in one direction and in another. So I've got a 3-dimensional object, and I've got to find the maximum point. Well, where that maximum point occurs is where, first of all, the slopes in every direction, in the x direction, and then maybe this is the y variable direction, or r and t, where that maximum occurs is a combination of what value of r, what value of t, and then what is the maximum profit. So we could use partial derivatives to try to understand that kind of problem a little bit better as well. But first, we need to understand what partial derivatives are and how they work.